pulse width modulation. The other day I might have told in the very beginning what is pulse width modulation. In the by definition, the width of the pulse is varied in accordance with the amplitude of the baseband signal. If the baseband signal amplitude is more, my pulse width is more. If the baseband signal amplitude is less, my pulse width is less. So this is my m of t. Let me take m of t, which looks like this. Let us suppose. So I have a pulse train. It will be all are having equal height and equal width. Then I have my pulse width modulated signal. Let me draw the pulse train again first, and then after that we'll draw the pulse width modulated signal. This is the same pulse train. I am redrawing it again, the second figure. So now let me change the color so that you can visualize more clearly. So here the amplitude of m of t is more, therefore my width of the pulse is increased. Now if I come here, it slowly decreases, right? My amplitude of the pulse is decreased. So compared to previous pulse width, now my pulse width is decreased. But compared to original pulse width of a unmodulated carrier, it is still increased. So as the time goes on, the m of t is decaying. So therefore, here I got the same pulse width of the unmodulated carrier pulse width. Then slowly again my m of t is decreasing. Therefore, my width of the pulse is decreased. Now again, slowly my m of t is increasing. Therefore, my width of the pulse is now increased. So whatever I have drawn in blue color is the pulse width modulated signal. And this red color is the unmodulated carrier. Carrier pulse train. So by definition, this is what pulse width modulation is. Now, the most important part is how to generate generation of PWM signal. So we take our M of t signal, or simply let me call it as S of t. S of t. Now is now passed through a circuit called sample and hold. Sample and hold circuit. So the output of sample and hold circuit, let it be S1 of t, is given to an adder to which my other input is S2 of t minus 1. I'll tell what is this S2 of t minus 1 little later. The output of adder is, let it be S3 of t, is given to a comparator. S4 of t. And this is my PWM signal, pulse width modulated signal. A little extension to this pulse width modulated signal, the block diagram. If I add one more block, if I add one more block called, say, monostable multivibrator. I'll tell this what monostable multivibrator. Then my output is called pulse position modulated signal. Let it be S5 of t. We'll come to that S5 of t part, that is PPM generation part later. Let us first discuss about PWM, that is S4 of t. How we could able to get that S4 of t pulse width modulated signal. So is this block diagram clear?
Yes, sir.
The same block diagram with little extension, addition of another block, what we call it as a monostable multivibrator. The output of monostable multi gives or produces pulse position modulated signal. So now let us try to get whether let us try to prove whether S4 of t is really generating pulse width modulated signal or not. So let me define first these S1, S2, S3, S4 first. What is S1? S1 is your M of t, or the message signal. Fine. Then what is S2? S2 of t is a sawtooth waveform. S2 of t is a sawtooth waveform. I don't know whether you know about how a sawtooth waveform looks like. Let me draw the sawtooth waveform. And have the sawtooth waveform something like this. Let it be what I can say, 0 or -1. This would be more convenient. So this is 0 and 1. Amplitude is 1, let us suppose. This is my S2 of t. But here in the block diagram, what I said is S2 of t minus 1. That means S2 of t minus 1 will certainly would be a signal whose DC level is shifted by minus 1. So therefore, it would look like something like this. This is my S2 of t minus 1. So S of t is the message signal. S2 of t minus 1 is the sawtooth waveform level shifted to minus 1. So its DC level is shifted to minus 1. Fine. Now, how to generate S3 of t? S3 of t, this is a simple adder circuit. Therefore, my S3 of t would be S3 of t equal to S1 of t, the output of sample and hold, S1 of t plus S2 of t minus 1 plus S2 of t minus 1. So this is my S3 of t. Can anyone tell me what is comparator? Comparator means what? What is comparator?
Which compares two signals.
Okay, then what is the output?
Difference.
Difference. Any comparator will have two inputs. One is the actual input signal and another one is the threshold. Keep remember. A comparator simply using an op amp or even BJT. I have a comparator here. And I said that my threshold value is 3 volts. Now, if the input signal, say M of t or S of t, if M of t is more than 3 volts, then my output signal is, say, 5 volts. If M of t is less than 3 volts, my output signal is 0. Did you get my point? Is that clear?
Yes.
So I'll get logic 1 or its equivalent 5 volts when M of t is greater than the threshold, that is 3 volts. And I'll get logic 0 or simply 0 volts when my M of t is less than 3 volts. Assume if my M of t is 2.5 volts, then what is the output voltage? For 2.5, output
0.
voltage would be 0. And assume my M of t is 3.85. For 3.85 volts input, my output would be
5 volts.
5 volts. Yeah, logic 1 or 5 volts. So the same the same principle here I am applying. So the input to the comparator is S3 of t. Input to the comparator is S3 of t. The output S4 of t is active high when the S3 of t is more than the threshold. If S3 of t is less than the threshold, then my S4 of t would become 0. So as long as S3 of t is greater than the threshold, my output is high. And as long as S3 of t is less than the threshold, my output is low. So this is what a comparator do. Then, do you have any idea about monostable multi?
No, sir.
Okay. Okay. What a monostable multi will do is we can trigger this monostable multi using an input signal. Then the monostable multi will generate, or the output of monostable multi will become active high for certain duration of time. Again, it get back to active low. Again, if I trigger with the input signal, then it will become active high after certain duration of time. Again, it get back to 0. We can as well design the monostable multi in active high position. When input trigger occurs, it will go to low for certain duration of time. Again, it will get back to active high. So this state is what we call it as quasi state. And this state is what we call it as stable state. A monostable multi has one quasi state, and all the remaining time it will be in the stable state. Now I'm saying triggering. Triggering means what? Triggering, maybe I can give active high, say +5 volts. Then it will generate one pulse. That's all. Again, if you apply +5 volts, again it will generate another pulse. Assume if my input signal is not DC, applying 5 volts, 5 volts, 5 volts, assume my input signal is something like this. So I can trigger my monostable multi with my negative edge. So when there is a transition from active high to active low, then the monostable multi will get triggered. A rectangular pulse of quasi-stable state will generate. Again, at this transition, positive to negative. So this is the negative edge triggering. This type of triggering is what we call it as negative edge triggering. During this interval of time, again another quasi-stable state will be generated. A rectangular pulse will be generated and return back to the stable state. This is the concept of what we call it as monostable multivibrator. So, okay. The advantage of this quasi-stable state, will take it into account in order to generate our pulse position modulated signal.